A common tool in image processing is a Fourier transform. Now that sounds like a big word, but basically what a Fourier transform does is it allows us to take a signal or a shape and turn it into a set of sine waves that can reproduce that particular shape. So here's a rather complicated shape, but if we look at this surface in terms of perhaps sine waves, we can see that there's a relatively long wave running through the surface. There's a bit of a medium wave hiding inside this surface. And then there's a very short wavelength hiding inside this surface. This breakdown into sine waves can be plotted. We can plot this in terms of wavelengths. We can look at each wavelength and see how much strength there is. So this is a wavelength content graph. At individual waves or wavelengths, we have some amount of amplitude, some amount of height. Now in the world of sine waves, amplitude would be the up part. For example, the top of the sine wave. So here we have this as our amplitude on that wavelength, and down here we might have a very tiny little amplitude of a sine wave here also. So the wavelength content chart can tell us how much of each wavelength we have. At the very shortest of wavelengths, at the tightly spaced surfaces or surface features, we have a small amount of amplitude. At the middle wavelengths, in this case, we might have a bit more amplitude, and in this particular surface that I've drawn, the very long wavelength has a bit more amplitude. So these wavelengths are hiding inside. So these wavelengths are hiding inside our surface, and mathematically we can pull them out. The SW parameter, calculated on roughness, waviness, or primary, takes our surface information and makes this graph and reports the wavelength where the highest amplitude occurred. So in this particular case, the strongest amplitude, the tallest bar in the wavelength content graph, would be related to a very long wavelength. So the wavelength where this occurred would be reported. Let's look at a different case though. Let's look at a surface that's kind of rough but has a strong wave in it. Perhaps in our machining process there was chatter. So this surface is a bit messy. It's not going to have pure wavelengths like perhaps the example I first drew. It will have this kind of wavelength content graph. It might have some roughness in it. It might have a very strong spike at one point due to this spacing right here, and then it may have some other things going on in it at the longer wavelengths. This wavelength content graph shows a strong amplitude right here. The wavelength where that occurred is some wavelength that's dominating. There's a dominant wavelength in this surface, and right here is the spacing that's associated with that dominant wavelength. So this spacing is reported right here on the wavelength axis of the wavelength content graph. We can use this math to determine what is the wavelength that's showing through the strongest in a signal. So the dominant wavelength is more practically used on the primary profile, where we're including all of the wavelength information. So in some cases we may remove a little bit of form and maybe look at a roughness kind of profile, but nonetheless, the tool dominant wavelength tells us if there is a strong sine wave hiding inside our data and what wavelength is that occurring at. And this will be reported in millimeters in terms of the x-axis of the data and the x-axis of the wavelength content graph. So to find a wave in your data, perhaps the SW parameter will be useful to you. And just remember to include all of the wavelengths you care about if you're choosing between roughness, waviness, or primary. Most commonly, primary is going to be your best tool.